Find somewhere comfortable tonight, somewhere your body can be heavy. You don't need to follow any of this closely, and you don't need to remember a word of it. Just let the sound of the words come and go, the way water moves over stone, without urgency, without destination. We're in no hurry here. If today was hard, you can set it down now. Whatever you carried through the hours, the small worries, the unfinished things, the conversations that played on repeat, none of that needs to come with you into this hour. It can wait somewhere outside the door. You don't need it tonight. We're going to spend some time together in a quiet and extraordinary place. Somewhere ancient and patient and built in the dark, grain by grain, over stretches of time so vast they make a human life feel like a single breath. A place that has been growing since long before anyone was watching, long before there were words for what it was. We're going to the reef. Not to study it, not to understand every piece of it. To let its slow, unhurried way of existing settle into you, the way sleep, when it finally comes, feels less like something you did and more like something you did and more. So rest now. Let your eyes close if they want to. Let the words arrive softly and drift away again. We have nowhere to be but here, and all the time in the world to get there. Imagine you are hovering in warm, clear water somewhere in the tropics. The light comes down in long, shifting columns from the surface above, bending and scattering as it descends, turning everything golden and blue at once. Below you, the seafloor rises in a landscape of extraordinary complexity. Ridges and towers and plains, deep-shadowed crevices and sudden bright open spaces. All of it covered in color so dense and varied, it seems almost impossible that any one place could hold so much of it. You might think you were looking at a rock formation. Something geological. Something made. The way mountains are made by pressure and time and the slow grinding of the earth. But here is the thing that stops people the first time they really understand it. None of it is rock. Every ridge, every tower, every gentle slope of that seafloor landscape is alive. Or rather, it was built by life. Built by animals. Tiny, soft-bodied, patient animals, each one no larger than a grain of rice, working in the dark and the shallows and the quiet for millions of years, laying down their calcium walls one microscopic layer at a time, leaving their skeletons behind when they died, and being replaced by their children, who built on top of them, and were replaced by their children in turn, and so on, across spans of time that stretch back to when the world was a genuinely different place. What you are looking at, hovering there in that warm and luminous water, is not a geological feature. It is the accumulated architecture of uncountable generations of tiny animals who never once stopped building. It is a coral reef. And the first thing to know about it, the thing that tends to produce a small, quiet shift in how you see the world, is that coral is an animal. Not a plant, though it can look like one, with its branching forms and its tendency to anchor itself in one place and reach toward the light. Not a rock, though its skeleton is made of the same calcium carbonate that makes limestone and marble. An animal, closely related in fact to jellyfish and sea anemones, to those slow, translucent, drifting creatures that you might have seen washed up on a beach or floating near the surface of a harbour, trailing their soft threads in the current. Each individual coral animal is called a polyp. And a polyp, at its most basic, is a small cylinder of soft tissue, open at one end, ringed with tentacles that reach out into the water to catch passing food. Tiny planktonic organisms, fragments of organic matter drifting by on the current. At the other end, the closed end, the polyp sits on the calcium carbonate cup that it has secreted from its own body. Its skeleton. Its home. The foundation of everything above it and everything to come. One polyp is almost nothing. A pinhead. A whisper of biology in an enormous ocean. But coral polyps do not live alone. They live in colonies, vast, interconnected communities of individuals, all sharing a continuous sheet of living tissue, all building their calcium cups in concert, all growing outward and upward together, generation after generation, century after century, adding their tiny contributions to a structure that eventually becomes something visible from space. The Great Barrier Reef, which runs along the northeastern coast of Australia, stretches for more than 2,300 kilometers. It is, by any measure, the largest structure ever built by living organisms on this planet, and it is the only animal-built structure on Earth that can be seen from orbit. A pale, intricate tracery along the edge of a continent, vast enough to have its own weather patterns, its own internal ocean currents, its own tides within tides. It was built by animals smaller than your thumbnail. The colonial corals that build reefs as we know them today have been at work for roughly 60 million years. The specific forms and species have changed across that time, shaped by mass extinctions and shifting seas and the slow drift of continents. But the basic impulse, the soft body, the calcium cup, the colony growing upward toward the light, has persisted. The reefs we know now, the ones that exist in their current form and location, are between 5,000 and 10,000 years old. Ancient by human measure, young by the measure of the earth itself. They are not finished. They are building still right now in the dark and the warmth of the shallow tropical sea, adding their fractions of a millimeter to structures that began when the last ice age was only just releasing its grip on the world, when the sea level was still rising, when the coastlines of continents were finding their current shapes. Somewhere out there, in the quiet deep of a warm ocean night, a polyp is secreting calcium, slowly, patiently, without urgency or intention, just building the way it has always built, the way its ancestors built before it, the way its descendants will build long after. The reef is patient in a way that is difficult to hold in the mind. But tonight, we have time to try. In the late 1830s, a young English naturalist named Charles Darwin found himself aboard a ship called HMS Beagle, somewhere in the vast warm reaches of the Pacific Ocean. He was in his mid-20s. He had already spent years at sea, watching the world from the deck and from the shore, filling notebooks with careful observations about things that other people had looked at and not quite seen. Darwin had a particular gift. He could look at something ordinary, a barnacle, a finch, a layer of sediment in a cliff face, and sense that it was telling a story, that if you looked at it long enough and thought about it carefully enough and connected it to the other things you had seen, the story would eventually reveal itself. When he looked at coral reefs, the story he found was one of extraordinary patience. He had no diving equipment, no underwater cameras, no sonar to map the seafloor beneath the ship. He could not descend into the reef and observe its structure directly. What he had was the view from the surface, the shapes of reefs as seen from above, from the deck of a ship or from a small boat rowed close to shore, and the geological reasoning he had been developing across years of observation. And what he noticed, looking at reef after reef across the Pacific and Indian Oceans, was that they came in three distinct forms. The first form hugged the coastline of an island directly. A fringing reef, he called it, a narrow band of coral growing close to shore, in the shallow water where the island's slopes descended into the sea. The island was still there, solid and volcanic, rising clearly above the waterline. The second form was separated from its island by a stretch of open water, a lagoon, calm and shallow, lying between the shore and the outer reef. The island was still present, still visible, but the gap between island and reef was notable. A quiet body of water that had not been there in the fringing stage. The third form was the most striking and the most puzzling to people who had not thought carefully about what it implied. An atoll. A ring of coral enclosing a lagoon of open water with no island at all. Just the ring. Just the coral, curved around an absence, surrounding a space where something had once been. Darwin's insight, arrived at without any instrument more sophisticated than a pencil and a notebook and a very good mind, was that these three forms were not three different kinds of reef. They were three stages in the life of a single reef. It began with a volcanic island rising from the ocean floor. Hot, new, still steaming perhaps, its slopes descending steeply into the warm, shallow water. Coral polyps settled on those slopes and began to build, close to shore, in the light. A fringing reef. Then the island began to sink, slowly, imperceptibly. Over thousands of years, the volcanic rock cooling and contracting, the ocean floor beneath it flexing gradually downward under its weight. As the island sank, the reef kept building upward, always chasing the light, always growing toward the surface. The distance between the sinking shore and the outer edge of the reef increased, filling with calm water. A lagoon formed, a barrier reef. And then, over further thousands of years, the island sank below the waterline entirely, disappeared into the deep. But the reef, still building, still growing upward, still reaching for the light, remained, tracing the outline of the island that was no longer there. A ring of coral around an empty lagoon, an atoll. There is something deeply moving about this idea, if you let it settle. The island is gone. The volcanic rock that the reef first clung to has long since descended into the darkness of the deep ocean. But the reef remembers its shape. The atoll is, in a sense, a memorial. A record written in calcium carbonate of something that once existed, preserved in the patient upward growth of animals that never knew they were writing history. Darwin published this theory in 1842 in a book called The Structure and Distribution of Coral Reefs. It was one of the first great works of his career, and it was largely correct. A remarkable achievement given that the geological processes he was describing would not be confirmed by direct observation for another century, when deep drilling into Pacific atolls finally revealed the volcanic rock far below the coral, exactly where Darwin had predicted it would be. What his theory revealed beyond the mechanics of reef formation was something more profound. Coral reefs were not simply biological communities, not merely collections of animals living together in the sea. They were records of geological time. Archives of the Earth's own slow movements, written in the language of accumulated calcium, preserved across millennia by the patient work of polyps that had no understanding of what they were recording. The reef does not know it is a clock. It does not know it is a memorial. It builds because building is what it does, in the light and the warmth, grain by grain, without any awareness of the vast story it is telling. Darwin understood that story by standing on the deck of a ship and watching very carefully for a very long time. Sometimes the most extraordinary insights come not from rushing toward an answer, but from being still enough and patient enough to let the answer find you. To understand how a coral reef is actually built, you have to go very small. Smaller than the reef, smaller than the colony, smaller even than the individual polyp. You have to go inside. A coral polyp, fully grown, is typically somewhere between 1 and 3 millimeters across. Soft-bodied, translucent, ringed at its open end, with tentacles that wave gently in the current like the petals of a tiny underwater flower. It sits in its calcium carbonate cup, its corallite, and from that fixed position it does two things simultaneously. It reaches outward into the water, catching food with its tentacles, drawing nourishment from the ocean around it. And it builds downward, secreting calcium, adding to the foundation beneath it, slowly deepening the cup in which it lives. The building happens in a specialized space between the base of the polyp's soft tissue and the surface of its existing skeleton. In this narrow, chemically active zone, the polyp draws calcium ions and carbonate ions from the surrounding seawater and begins to manipulate them. It pumps hydrogen ions away from this space, raising the pH, increasing the concentration of carbonate ions until conditions are right for crystallization. And then, slowly, the ions bond. Calcium and carbonate lock together into a crystalline structure called aragonite, a form of calcium carbonate that is harder and denser than chalk, closer in nature to the minerals that make up marble. This is calcification. The polyp is not so much growing its skeleton as manufacturing it, running a precise chemical process in a tiny factory no larger than a cell layer, producing crystals that accumulate grain by grain into the rigid walls of its home. By itself, this process would make coral a slow and modest builder. Interesting, certainly. Remarkable in its way. But not capable of producing the vast structures we are describing. Not capable of building a barrier reef 2,000 kilometers long. What makes the reef possible? What transforms a modest animal into an architect of cathedrals is a partnership, and it is one of the most intimate and extraordinary partnerships in the natural world. Living inside the tissues of a coral polyp, woven into the very cells of its body, are microscopic algae called zooxanthellae. They are dinoflagellates, single-celled organisms, ancient and simple, capable of photosynthesis. They live not on the surface of the coral, but within it, sheltered inside the polyp's own cells, surrounded by the coral's living tissue. In exchange for this shelter, and for access to sunlight, and for the carbon dioxide and nitrogen-rich waste products that the coral produces, the zooxanthellae do something remarkable. They photosynthesize. They take the sunlight filtering down through the water and use it to convert carbon dioxide and water into sugars and oxygen the way any plant does, and then they pass the products of that photosynthesis, glucose, glycerol, amino acids, directly to their host, directly to the coral. Up to 90% of the coral's energy needs can be met this way. The polyp is, in a sense, farming sunlight, using its algal partners as solar panels embedded in its own tissue, harvesting the energy of the sun from inside its own body. And this partnership does something else, something that transforms the reef's rate of construction entirely. When the zooxanthellae photosynthesize, they consume carbon dioxide. This consumption shifts the local chemistry in ways that favor calcification. It creates conditions in which calcium and carbonate ions are more readily available, in which the precipitation of aragonite crystals happens more easily and more quickly. The result is that corals with their zooxanthellae build their skeletons dramatically faster than they would without them. A coral in full sunlight, with its algal partners working at capacity, can calcify several times faster than a coral in the dark. This phenomenon is called light-enhanced calcification. And it is why tropical reefs, bathed in intense equatorial sunlight, their polyps full of photosynthesizing zooxanthellae, can build structures of such scale. The sunlight is not just illuminating the reef, it is, in a very real sense, building it. The precise mechanism by which zooxanthellae accelerate calcification is, beautifully, not fully understood. Scientists know the broad outlines, the chemistry, the energy transfer, the connection between photosynthesis and calcification rates, but the exact cellular and molecular details of how the algae and the coral communicate, how the algal chemistry influences the polyp's own building process, remain a subject of ongoing investigation. There is something quietly wonderful about that. One of the most productive biological partnerships on Earth, responsible for some of the largest structures built by life, and science is still learning its deepest secrets. The zooxanthellae also give the coral its color. The vivid greens and browns and golds of a healthy reef are, in large part, the colors of the algae living inside the coral's tissue. When a coral is stressed by water that is too warm or too acidic or too full of the wrong nutrients, it expels its zooxanthellae. The color drains away. The coral turns white. This is coral bleaching, and it is a sign that the partnership has broken down, that the coral has lost the partner that provides most of its energy, that it is now running on reserves and will starve if conditions do not improve. But in the warmth and the light of a healthy tropical sea, the partnership thrives. The zooxanthellae photosynthesize, the coral builds, the calcium cups accumulate, the colony grows upward toward the light, following the sun the way a garden follows the seasons, slowly, unhurriedly, adding its fractions of a millimeter each day, each week, each year, across the patient centuries. Every coral reef in the world began with a single event so small it is almost impossible to picture. A fertilized egg drifting in open water, smaller than a full stop on a printed page. Carried by currents, warmed by sunlight filtering down from above, already carrying within its cells the instructions for everything that would follow. Coral reproduction is a remarkable thing. Many coral species reproduce sexually through a process called broadcast spawning, and it happens on a schedule so precise it seems almost planned, once a year, on a night determined by the temperature of the water and the phase of the moon. Typically, a few nights after a full moon, in the warmth of late spring or early summer, an entire reef will spawn simultaneously. Clouds of eggs and sperm rise from the coral surface in a slow, upward blizzard, drifting toward the surface in a haze of pale spheres, filling the water column with the raw material of the next generation. The eggs and sperm from different colonies meet in the water column and fuse. A fertilized egg becomes a planula, a tiny, free-swimming larva, oval and ciliated, covered in fine hairs that beat rhythmically to propel it through the water. The planula drifts. It may travel for days or weeks, carried by currents, descending and rising, searching, finds or pettily use or weeks what it is searching for. Or rather, what it is responding to is a chemical signal. The sea floor around a coral reef is often covered in a crust of pink coralline algae, a separate organism that cements the reef's framework together and whose presence releases chemical compounds into the water. When a planula larva encounters these compounds, something changes in its behavior. It begins to orient toward the bottom. It becomes drawn downward, toward the substrate, toward the specific chemical signature of a place where coral has already been growing. When it finds its surface, the right texture, the right chemistry, the right angle of light, the planula settles. It attaches, and in the space of a few hours, it transforms. The free-swimming larva becomes a polyp. It secretes its first tiny disc of calcium carbonate. It extends its first tentacles. It begins to feed. And then it begins to bud. Budding is how a coral colony grows. The founding polyp divides, not sexually, but by splitting itself, producing a genetically identical copy that grows alongside it, connected by a shared sheet of living tissue. That copy divides, and the copies divide, and the colony expands outward and upward in a pattern determined partly by species and partly by the conditions of its environment. Some species grow in branching forms, reaching outward like the fingers of a spread hand. Some grow in rounded domes, their surface covered in a maze of ridges and valleys. Some grow in flat plates, maximizing their surface area in the direction of the light. All of them are, in a fundamental sense, one organism. The individual polyps of a colony are connected by their shared tissue, sharing nutrients, sharing chemical signals, responding together to changes in light and temperature and water chemistry. And it grows slowly, very slowly. Massive corals, the large, rounded, dome-shaped species that form the backbone of many reef structures, typically add somewhere between 3 millimeters and 2 centimeters to their diameter each year. In a good year, in warm, clear, nutrient-rich water, perhaps a little more. In a difficult year, perhaps less. The average, across centuries, tends toward the modest end of that range. Consider what this means for a coral head the size of a car. A large, rounded colony of brain coral or star coral, perhaps 1.5 meters across, sitting on the reef floor with its maze of ridges and the slow pulse of its polyps feeding in the current. At a growth rate of 1 centimeter per year, that colony has been building for something in the neighborhood of 150 years. At 3 millimeters per year, it might be 5 centuries old. There are coral colonies that are thought to be over 1,000 years old, growing when the medieval period was still in progress, growing when the continents of the Americas were unknown to European cartographers, growing when the languages spoken in most of the world's cities were entirely different from the ones spoken there today, just building quietly in the warm water, adding their fractions of a millimeter, unaware of the centuries accumulating above them. And here is something that deepens this image further. Coral colonies do not age in the way that most animals age. They do not accumulate the cellular damage and the declining function that we associate with growing old. They regenerate constantly, replacing damaged tissue, maintaining their living layer at the surface of their ever-growing calcium skeleton. A coral colony is, in a biological sense, potentially immortal. The individual polyps at its surface are young. The skeleton beneath them is ancient. The colony as an entity persists, neither young nor old, simply continuing. The colony does not experience time the way we do. It does not feel the centuries passing. It does not know it is ancient. It simply builds the way it has always built, adding its quiet increments to a structure that began with something no larger than a grain of sand, drifting in warm open water, following a chemical signal toward the seafloor, finding its place and beginning. Step back now from the individual colony. Step back further still until you can see the reef as a whole. The entire complex, sprawling, three-dimensional landscape of calcium and color and shadow and light. What you are looking at is not simply a collection of coral colonies growing side by side. It is a city. Not a city in the human sense. Not planned, not organized around commerce or power or the movement of people. But a city in the sense of density and complexity and the interlocking of countless lives, each one dependent on the others, each one occupying a specific niche in a structure that provides for all of them. Coral reefs cover less than 1% of the ocean floor. The entire global reef area, if you could gather it all into one place, would fit within a region roughly the size of France. And yet within that tiny fraction of the sea's total surface, somewhere between 25 and 30% of all marine species on Earth make their lives. Every shape of fish, every color of invertebrate, every variety of worm and crab and mollusk and sea star and eel and shark. The diversity packed into a reef ecosystem is, by any measure, extraordinary. The calcium carbonate skeleton of the reef creates this diversity by creating space. Crevices and overhangs and tunnels and caves, broad open plains and sudden vertical walls. The intricate maze of a coral head's ridged surface and the dark enclosed passages beneath a large colony's base. Each of these microhabitats is a different world, with different light levels, different water flow, different food availability. And into each one, over thousands of years of evolution, a specific community of organisms has moved, adapted, specialized, and made itself a home. But the reef is not only a structure of accumulation, it is also a structure of constant erosion. And this balance between building and breaking down is one of the things that makes it so dynamic and so alive. Parrotfish, with their fused beak-like teeth, bite directly into the coral skeleton, scraping off chunks of calcium carbonate to get at the algae growing within and upon it. The calcium carbonate passes through their digestive systems and is excreted as fine white sand, the same white sand that covers the beaches of tropical islands, that sifts between your toes and catches the light in the shallows. A single large parrotfish can produce hundreds of kilograms of sand per year. The white beaches of the Maldives, of Hawaii, of the Caribbean islands. They are, in considerable part, the digested remains of coral skeletons processed by fish and deposited by currents over centuries. Sea urchins rasp at the reef surface with their complex five-toothed mouths, grinding down the calcium carbonate, creating depressions and holes. Boring sponges, aptly named, dissolve their way into the coral skeleton using chemical secretions, hollowing out passages that weaken the structure from within. Worms and mollusks drill through the calcium for shelter. All of this erosion serves the reef. The broken down material becomes sand, which fills spaces, which provides substrate for new settlement. The holes and passages created by burrowing animals become homes for other animals. The dynamic interplay between building and breaking creates the complexity that sustains so much life. And then there are the corals that build where no sunlight reaches at all. Deep sea corals. Cold water corals grow in the dark, far below the sunlit zone where the tropical reef builders make their home. They have been found as deep as 2,000 meters, in water as cold as 4 degrees. Without sunlight, they have no zooxanthellae, no algal partners, no light-enhanced calcification. They grow slowly even by coral standards, adding fractions of a millimeter each year, building their calcium frameworks in the cold darkness by filtering through from the currents that move through the deep ocean. They build reefs of their own, down there in the dark. Structures that can be hundreds of meters tall, that take tens of thousands of years to grow to significant size, that support their own communities of deep-sea species. They are almost never seen by human eyes. They go about their building in complete darkness, in the deep cold, with the same patient persistence that characterizes all coral construction. There is something quietly remarkable in that, the impulse to build, the polyp's fundamental act of secreting its calcium cup, of adding its fraction to the whole, runs deeper than sunlight, deeper than warmth, deeper than the conditions we associate with the vibrant tropical reef. It persists in the cold and the dark, 2,000 meters down in one of the most remote and inhospitable environments on Earth. The reef is not just a tropical phenomenon. It is something closer to a universal tendency. Life, given the right chemistry and enough time, will build. For a long time, the story of coral reefs and the planet's climate was told in one direction. Reefs, it was understood, were sensitive to climate, vulnerable to warming seas, to rising acidity, to the shifting chemistry of an ocean absorbing more carbon dioxide than at any time in recent geological history. The reef was a patient, passive recorder of what the climate was doing, a living archive of environmental change, a canary in the coal mine of a warming world. This understanding was not wrong, but it turned out to be incomplete. In December of 2025, researchers at the University of Sydney and the Université Grenoble-Alpes published a study in the Proceedings of the National Academy of Sciences that reframed the relationship between coral reefs and the Earth's climate in a fundamental way. The lead researcher was Associate Professor Tristan Sales, and the team brought together an unusual combination of tools: plate tectonic reconstructions, global surface process models, climate simulations, and ecological modeling to trace the history of shallow water carbonate production all the way back to the Triassic period, 250 million years ago. What they found was not a story of reefs as passive recorders of climate. It was a story of reefs as active participants in it, as regulators, as a slow geological thermostat built from the accumulated calcium cups of animals the size of a grain of rice. Here is the mechanism, in the gentlest possible terms. When coral reefs flourish, when tropical seas are warm and shallow, and the continental shelves are wide, and the conditions for reef growth are favorable, enormous quantities of calcium carbonate accumulate in the shallow oceans. The reef is building, and building fast, pulling calcium and carbonate ions out of the seawater and locking them into solid limestone. This process has an effect on the ocean's chemistry. It reduces the ocean's capacity to absorb carbon dioxide from the atmosphere. And when the ocean absorbs less carbon dioxide, the planet's recovery from any large carbon disturbance, a volcanic eruption, a mass extinction event, anything that pumps large quantities of carbon dioxide into the atmosphere, is slower. The reef, in its flourishing, paradoxically slows the planet's ability to return to equilibrium. Now consider the opposite. When reef space collapses, when tectonic shifts narrow the tropical shelves, when sea levels drop and expose the reef to air, when conditions deteriorate and the reef cannot maintain its building rate, something interesting happens in the ocean's chemistry. Calcium and alkalinity begin to build up in the seawater, no longer being drawn out by reef construction. This increase in alkalinity makes the ocean a more efficient absorber of atmospheric carbon dioxide. And it stimulates the growth of tiny calcifying organisms called nanoplankton in the deep ocean, which begin to produce their own calcium carbonate structures in the deep water, burying carbon in the sediment of the seafloor. The result, when reefs collapse, the planet recovers from carbon disturbances faster. This is counterintuitive, and it is worth sitting with for a moment. The flourishing of the reef, the thing we think of as the healthy state, the vibrant, biodiverse, productive state, actually slows the planet's self-correction mechanism when it comes to carbon. And the decline of the reef, the thing we rightly mourn, can in certain geological circumstances accelerate that mechanism. The researchers found that the Earth's climate system has oscillated between these two modes across the past 250 million years, with the distribution of tropical reef habitat controlled by the slow drift of continents, the rise and fall of sea levels, the opening and closing of seaways, acting as a kind of switch between them. The reef is not a passenger in the story of the Earth's climate. It is one of the authors. This is a remarkable thing to contemplate in the quiet of a late night. The idea that an ecosystem built by animals smaller than a fingernail has been actively shaping the chemistry of the atmosphere and the ocean across geological time, that the calcium cup of a coral polyp multiplied by trillions and accumulated across 250 million years is part of the mechanism by which this planet regulates itself. That the reef is not just beautiful, not just biodiverse, not just economically valuable, but fundamentally woven into the way the Earth stays habitable. Every polyp building in the dark is, without any awareness of the fact, participating in a planetary process that has been running since before the dinosaurs. The scale of that participation is impossible to fully grasp, but it is there, quiet and vast, in every calcium crystal being laid down tonight in a warm tropical sea. The reef builds. The planet breathes. They have been doing this together for a very long time. Somewhere in the warm, clear water off the coast of Florida, or in the Caribbean, or in the vast blue reaches of the Indo-Pacific, there is a person underwater right now, or was in the recent past, and will be again tomorrow, tending a garden that most people will never see. The garden is not large. By the standards of the reef, it is trying to help restore. It consists of a series of simple structures, lengths of wire and rope, suspended horizontally in the water, a few meters below the surface, hung with small fragments of living coral. The fragments dangle on short lines, swaying gently in the current, each one a few centimeters long, each one a living piece of a colony that was clipped from a healthier part of the reef, or from a coral nursery, or from a donor colony maintained specifically for this purpose. This is coral gardening. And it is, in its quiet way, one of the most hopeful things happening in the ocean. The idea is straightforward. Coral grows slowly, but it does grow. If you take a small fragment of living coral, a branch tip, a piece of tissue attached to a small section of skeleton, and give it a stable place to grow in good conditions, it will continue building. It will add its fractions of a millimeter each day. Over months, it will become a small but viable colony. And then it can be transplanted, carefully, by hand, by a person in a wetsuit hovering above a degraded reef section onto the sea floor, where it will attach, grow larger, and begin to contribute to the reef's recovery. The people who do this work describe it with a particular kind of quiet patience. They are not fixing the reef quickly. They know they are not fixing it quickly. A coral transplanted today will take decades to grow to significant size, and the reef it is contributing to may take centuries to fully recover. The gardeners working in these nurseries today will not see the result of their work in any final sense. Neither will their children, most likely. What they are doing is more like planting a forest than repairing a building, an act of faith in a future they will not live to witness, grounded in a care for something they love deeply in the present. Noah's Restoration Center, along with a growing network of reef nurseries operating across the Caribbean, the Pacific, and the wider Indo-Pacific, has been refining and expanding these techniques for years. The nursery trees, those simple wire and rope structures, have been joined by more sophisticated approaches. Some nurseries now grow coral fragments on specially designed ceramic or concrete substrates that mimic the texture of natural reef rock, making transplantation easier and survival rates higher. And then there is the spawning work. Once a year, on those warm and moon-guided nights when the reef releases its clouds of eggs and sperm into the water column, researchers are there with collection nets and containers, gathering the genetic material of multiple colonies from across a reef system. The eggs and sperm are allowed to fertilize in carefully controlled conditions. The resulting planula larvae are raised in land-based tanks, fed and monitored and kept at optimal temperature and salinity, allowed to settle and begin their growth in an environment free from predators and physical disturbance. The goal is genetic diversity. A reef that has been damaged by bleaching or disease may have lost many of its colonies, leaving the survivors genetically similar to one another, less resilient to future stresses. By raising large numbers of genetically diverse new individuals from the spawning of multiple parent colonies, researchers can reintroduce that diversity when the young corals are eventually transplanted back to the sea. It is painstaking work. Each individual coral must be tended, monitored, checked for signs of disease or stress. The survival rates, even with careful management, are far from perfect. The ocean is a complex and demanding environment, and a small coral fragment newly transplanted onto a degraded reef faces challenges that no amount of human care can entirely eliminate. But the people doing this work keep doing it. They return to the water day after day, tending their underwater gardens with the same unhurried dedication that the reef itself brings to its own construction. They know the full result will not arrive in their lifetime. They tend it anyway. There is another reason this quiet rebuilding matters beyond the ecological and the aesthetic. Coral reefs are, it turns out, a pharmacy. The organisms that live within them, the corals themselves, the sponges, the algae, the bacteria, have evolved over millions of years a remarkable array of chemical compounds that serve as defenses against predators, as signals to potential partners, as weapons in the competition for space on the reef. And many of these compounds have turned out to be extraordinarily useful in human medicine. Compounds derived from coral reef organisms are currently under investigation as potential treatments for cancer, for bacterial infections, for arthritis, for heart disease, and for Alzheimer's disease. Some have already been developed into approved medications. The reef is not only an ecosystem and a geological record and a planetary thermostat, it is a library of biochemistry, accumulated across millions of years of evolution, that humanity has barely begun to read. Every coral fragment growing on a nursery tree, every young colony being raised in a land-based tank, is a small part of that library being preserved. The gardeners underwater are not only tending an ecosystem, they are tending a future that extends in directions none of us can fully anticipate. They work slowly. They work with care. They work the way the reef works, grain by grain, in the quiet, for a result that will outlast them by centuries. Come back now to the very beginning, to the image we started with. A single polyp, soft and small, no larger than a pinhead, sitting in its calcium cup at the bottom of a warm, shallow sea, somewhere in the tropics, in the dark of an ancient night. Its tentacles are extended, moving gently in the current, alert to the drift of whatever food the water might carry past. Beneath it, in the narrow chemical space between its soft tissue and the crystal surface of its skeleton, the slow work of calcification is underway. Calcium ions and carbonate ions, drawn from the surrounding water, are being assembled, grain by grain, into aragonite crystal, by an amount that no instrument available to that first polyp could measure, by an amount that no instrument available to us tonight would register as significant. And yet, the Great Barrier Reef began this way. Not with a grand gesture, not with a dramatic event, but with something exactly this small. A planular lava following a chemical signal toward the seafloor. A moment of settlement. A first calcium cup. A first bud. the beginning of a colony that would, across thousands of years and billions of individual acts of calcification, contribute to a structure visible from space. This is the thing the reef teaches, if you spend time with it long enough to hear it. Not speed, not force, not the dramatic accumulation of large things in short times. The reef teaches the power of the imperceptible increment. The grain of calcium laid down tonight that is indistinguishable from nothing, but is not nothing. The fraction of a millimeter added this year that brings a 500-year-old colony to the size it will be when the next century arrives. The patient, unhurried, grain by grain accumulation of something vast from something almost too small to see. Researchers at Brighton and Sussex Medical School have found something that connects this ancient rhythm to the one happening inside you right now as you rest. When people listen to natural soundscapes, the gentle movement of water, the quiet ambient sounds of a living environment, something measurable happens in the body. The nervous system shifts away from the alert, scanning, ready for action state that the demands of a day produce, and toward the slower, softer state in which the body can repair and restore itself. Heart rate drops. Breathing deepens. The brain's activity, as seen in imaging studies, becomes more stable, more settled, less driven by inward-focused worry, and more open to the kind of diffuse, wandering attention that precedes sleep. The sounds of the ocean, the gentle rhythms of water moving, the soft ambient hum of a living reef, are interpreted by the brain as safe, as non-threatening, as the sounds of a world that is, for now, at rest. And the brain, receiving that signal, begins to rest too. There is something in this that feels important, though it is hard to state directly. The reef and the sleeping body are doing something similar. Both are engaged in a process of accumulation so slow it cannot be observed in any single moment. Both are building something vast from increments too small to register individually. Both require, above all, patience, the willingness to allow the process to unfold without forcing it, without rushing it, without demanding that it happen faster than it naturally can. Sleep does not come when you pursue it. Anyone who has lain awake in the small hours, willing themselves to fall asleep, knows this. Sleep comes the way the reef grows, not through effort, but through the accumulation of small quiet moments, each one almost identical to the one before, each one adding its imperceptible fraction to the whole, until at some point that cannot be precisely identified, something has crossed a threshold. The coral head has grown from the size of a coin to the size of a fist. The person lying in the dark has moved from wakefulness to something softer, something deeper, something that is no longer quite wakefulness at all. The reef does not know it is building. The polyp has no awareness of the structure accumulating beneath it across the centuries. It simply does what it does in the warmth and the dark and the quiet, following the chemistry of its nature, adding its grain to the whole. You do not need to know you are sleeping. You do not need to track the process or manage it or ensure it is happening correctly. You can simply allow the quiet to accumulate around you the way calcium accumulates in a coral cup, grain by grain in the unhurried dark. Think of the deep-sea corals building in complete darkness 2,000 meters down in water barely above freezing, with no sunlight and no algal partners and no warmth to speed the process. Just the slow, patient chemistry of calcification, proceeding at its own pace in conditions that seem entirely inhospitable to anything as delicate as growth. And yet the structures they build are real. They are there. They rise from the sea floor in the cold dark, hundreds of meters tall, teeming with life, built across timescales that dwarf the entire span of human civilization. Whatever you are carrying tonight, whatever the day left behind in your body, whatever the mind is still turning over in the quiet, It does not need to be resolved before you sleep. The reef does not wait for perfect conditions. It builds in the cold, in the dark, in the storm and the calm alike, because building is simply what it does. Rest is simply what you do. It does not require your management. It only requires that you stop insisting on something else. Somewhere in a warm tropical sea right now, a coral polyp is secreting calcium. The amount it adds tonight is immeasurable, but it is not nothing. Across 1,000 years, across 1,000,000 generations of polyps doing exactly this, it becomes a structure visible from space. The night is doing the same for you. Each quiet breath, each moment the body releases a little more of its held tension. Each second the mind drifts a little further from the noise of the day. You don't need to feel it happening. The reef doesn't feel itself growing either. It just grows. And so the night continues, soft and vast and ancient, holding you the way the ocean holds the reef, completely, without effort, with a patience that has no end in sight. Somewhere behind you, the day has already grown distant. Let it stay there, far off, fading into the dark, like an island slowly sinking below the waterline, leaving only the calm lagoon of this quiet hour. Drift now, if you're ready. Sleep well.